Okay, good day everyone, and welcome to lecture 11 of 124-105. Might as well start the lecture. Some introduction in the beginning here. So we are still continuing from what we started yesterday. Yesterday we started the topic on magnetic field. We learned that if you have a magnet, the magnet will set up a magnetic field around itself, much like a charge setting up an electric field around itself. And we learned that if you have a magnetic field and you have a charge with some charge Q moving in that magnetic field region, then that moving charge with velocity V will experience a magnetic force, right? So that was the main, the key idea in yesterday's lecture. You need to have a moving charge in a magnetic field region in order to have a magnetic force, for that charge to feel a magnetic force. And then we went on to learn about one of the applications of the force experienced by a moving charge by looking at the velocity selector and mass spectrometer. And then we looked at, we saw that if the charge moves in a uniform magnetic field region, well, like here in this picture, we know that the magnetic field is uniform because the magnetic field lines represented by this X's, showing that the magnetic field is into the page, they are evenly spaced or equally spaced. So you have a uniform magnetic field in this region here. If you have a charge with some velocity V entering that uniform magnetic field region, we learned yesterday that there is a centripetal, the magnetic force acts like a centripetal force, and it actually makes the charge move in a circular motion. So we related the centripetal force to the magnetic force. Centripetal force is mv squared over r. Magnetic force magnitude from this definition here is QVB, and then from there we can relate the radius. Again, when we're talking about radius, it's just half of this distance here that gives you the radius, and by measuring the radius of the charge with known speed V, we are able to determine the mass, and that then allows us to identify an unknown charge or unknown ion. So we looked at that conceptually, but we didn't have time to look at the numerical example of the velocity selector and mass spectrometer. So you can read this long introduction later on in your own time. Essentially, it's just saying what a mass spectrometer is used for. The most important information you can pick up here is that you have a charge of positive E. Right. Yeah, so there's a charge of plus E. E, again, the elementary charge, 1 times 6 times 10 to the negative 1.6 times 10 to the negative 19 coulombs, right? You have a plus E charge that goes into the velocity selector here, which then the velocity selector selects the charges with the correct speed or velocity and lets them enter this detector region. So there are 2 parts there. The first question is in regards to the velocity selector. It asks us to determine the magnitude and direction of the electric field, right? You'll only have an electric field in the velocity selector part, such that the fragments of charge that are moving at this specific speed, 1.2 times 10 to the 5 meters per second, they will pass right through the velocity selector undeflected. Okay. And so meaning the forces in the velocity selector balance each other out. Yeah, we know that you have this moving charge. It will enter this magnetic field region. So this X indicates that there's magnetic field there. The magnetic field is 18 millitesla as given, right? So we know that there is some magnetic force that this moving charge will experience when it enters this magnetic field region of the velocity selector. right? And I'll so you have a magnetic field of that exerts a magnetic force on the charge. In your velocity selector, there should also be an electric field, and hence that's why the problem is asking you to calculate the electric field, because the electric field will then exert an electric force on the moving charge. If you expand these definitions, magnetic force is QVB, right? For the magnitude that's coming from this vector product here or cross product there. And the electric force, we learned that to be equal to charge times the electric field. Okay, we're talking about the same charge that experiences the force, and hence Q will cancel on both sides of the equation. And therefore, we are able to find the electric field. The speed is given 1.2 times 10 to the 5, and simply multiply that to the magnetic field in the velocity selector, which is given as 18 times 10 to the minus 3 Tesla. Right. So just plug that into your calculators. You'll find the answer is 2160 newtons per coulomb. That's for the magnitude. Now to find the direction, okay? To find the direction, you can either, if you know the charges on the plates, right, then you can find the direction of the electric field, but the charges on the plates are not indicated, right? It's not given which plate is positively charged and negatively charged. So you sort of have to work your way through the direction of the electric field by figuring out first what's the direction of the magnetic force, because we have all the information we need to find the direction of the magnetic force. You know that the velocity vector is in the I hat direction, and the magnetic field is into the page, right, or minus K hat direction. Hence, by taking the cross product, because force is equal to QV cross B, you need to cross the velocity vector into the magnetic field vector. Your answer will be J hat, because it's the only unit vector that's not involved in the cross product. Okay, you have I hat and minus K hat in the cross product. So the answer will automatically be J hat, whether it's positive or negative depends on whether you crossed in the clockwise or anti-clockwise direction. Since you crossed V to B in the anti-clockwise direction, that will be a plus J hat for your magnetic force, right? So essentially, once your charge enters here, you have a magnetic force that's upwards. You know that the electric force needs to balance out that magnetic force. So the magnitude should be equal, but the direction for the electric force should be opposite the direction of the magnetic force, right? Hence, the direction should be negative J hat or downwards. Right. And once you figured out the direction of the electric field and therefore the electric force, you can then assign that, you know, this plate on top is positively charged, while the plate at the bottom is negatively charged, because we learned that electric fields go from positive charges to negative charges, right? And since your charge is positive, the electric force is in the same direction as the electric field. Good. Right. Okay, so for the second question, it says there, now you have these fragments of plus E charge, whose speed is 1.2 times 10 to the 5 meters per second. They now pass through the velocity selector undeflected, and they encounter this detector region. Okay, so the detector region only contains a magnetic field that's uniform throughout the detector region, and that causes a circular motion for the charges that reach the detector region. The question is asking you to find the mass of the fragment, the charge that reaches the detector region. Well, they gave you the answer, but your solution should show that the mass is 2.2 times 10 to the minus 26. Right, so just use a clean page here. So you have there the plus E charge that passes undeflected through the velocity selector. Initially, it reaches the detector region with a speed or velocity in the positive I hat direction, right? So if you do right-hand rule, right, once again, you have velocity in the I hat direction and you have magnetic field in the negative K hat direction. That means that your charge encounters a magnetic force in the J hat direction, okay? But then when you do the crossing from V to B, you're crossing anti-clockwise, hence that's a positive magnetic force. So what happens is that your charge here is pulled upwards by the magnetic force, okay, and then pulled upwards and then pulled to the left. Right. At this point, you have a velocity that's moving upwards, a magnetic field that's into the page. So that results to a magnetic force to the left. Or essentially, your charge will follow this semicircular path. Okay, it's semicircular because it's stopped by the detector right here. Okay. What's given is that the distance from the slit to the point where the particle is detected, this is 11.6 centimeters. Okay. Right, but we know that the centripetal force of the circular motion is provided by the magnetic force on the moving charge. Hence, mv squared over r is equal to qvb. You want to find the mass, right? The speeds will cancel out. And so the mass is equal to QRB over V speed. And you know everything, charge of an electron 1.6 times 10. Oh yeah, the plus E, sorry, it's not an electron, but a proton. 1.6 times 10 to the negative 19 coulombs times the radius. Now be careful with the radius because what's given is the distance from the slit. Okay, this is the slit here where the particle entered the detector region. It's the transverse distance from the slit to the point where it's detected. So 11.6 centimeters is actually the diameter. Right? Diameter of the circular path is 11.6 centimeters or 0.116 meters. So the radius should be half of that. Right? And the magnetic field is given there, 280 millitesla. And then the speed is the speed of the particles that entered, which was given in the first question, 1.2 times 10 to the 5 meters per second. Right. Plugging that into your calculator should give you the mass as indicated in the question. Good. All right, any question there? So are we okay with velocity selectors and mass spectrometers? Yeah, okay. Yeah, I hope so. Right, so these examples showed us that if you have a charge that's moving in a magnetic field region, that charge will experience a magnetic force. But we also learned that charges that move, they actually create currents. So a current is nothing but a charge that's moving. So therefore, if we combine those two concepts together, current being a moving charge and a moving charge experiencing a force in a magnetic field region, then it sort of makes sense that if you have a wire that has current flowing through it and you put that wire in a magnetic field region, then that wire will experience a magnetic force. And the magnetic force that wire experiences is given by this equation. I, of course, is the current in the wire. Okay, L is the length of the wire, B is the magnetic field. So if you compare that to the force of a moving charge, it's QV cross B, right? Then it's also cross product. So all the strategies we learned for finding the force of a moving charge can be used to find the force of a current carrying wire. So first you can find the magnitudes of the force on the wire, okay, by expanding the cross product into its sine theta function, right? L, that's the length of the wire that has current, and B is the magnetic field. And again, for the direction, you use the right-hand rule, the same right-hand rules that you use for finding the direction of a moving charge in a magnetic field. Right. Cool. So say, for example, you have this wire, it carries a current I, right, in the direction of plus I hat. Okay, and there's a magnetic field around the wire. The magnetic field is directed into the page, minus K hat, as indicated by this cross here. Okay, what's the force, magnetic force experienced by this wire? And magnetic force is defined as the cross product between the length and the magnetic field vectors, right? So for the direction of the length, you take the direction of current flow, and that's what you put in the right-hand rule for the direction of the length. But for the magnitude, right, expand the cross product to its sine theta definition, okay? So we're working with variables here because we're not given numerical values for the currents. So the current is still I, the length of the wire is L, and the magnetic field strength is B0. Yeah, so you have the B0 there, the magnitude of the magnetic field. Theta is the angle between the two vectors in your cross product equation. So that means it's the angle between the length or the direction of the current, okay, which is plus I hat, and the direction of the magnetic field vector, which is minus K hat, right? So those two vectors, they're actually perpendicular to each other, right? So you have this I hat and minus K hat is actually into the page, but you can see that the angle is 90 degrees. So essentially the magnitude is ILB. And then for the direction, you do the cross products. So you have I hat crossed with minus K hat. That will naturally give you J hat, but you're doing the crossing in the anti-clockwise direction. So that's a plus J hat or upward direction. Good. Right, how about in this case where you now have the magnetic field that is at 30 degrees relative to the direction of current flow. So you have here the current, it's flowing to the left. You have a straight current carrying wire. You immerse it in a magnetic field of magnitude B0 at an angle of 30 degrees. What's the force experienced by this wire? Both magnitude and direction. Right, magnitude is relatively straightforward. IL cross B expanded to ILB sine theta. Theta, again, that's the angle between the magnetic field and the current. It's straightforward because it's given there as 30 degrees. So you can find the magnitudes of the force on the current carrying wire. For the direction, okay, it's the same strategy that we used before. Whenever you have a vector that's diagonal, you can always break this diagonal vector into its horizontal component, I hat, and its vertical component, J hat. Okay. right? And then you do the cross product of the current to each of the components of the diagonal vector there. So you're essentially getting minus I hat crossed with I hat plus j hat. Okay. And if you're crossing the same unit vectors like I hat crossed with I hats, or even if it's negative, it's 0, because as you can see, right, the x component is parallel or anti-parallel to the current direction. So this crossing is equal to 0. So you're effectively just crossing minus I hat with j hat. So you're doing this cross product here, minus I hat for the current and j hat. Okay, the answer is, of course, obviously k hat, but you're doing the cross in the clockwise direction, so that will be a minus k hat. And let me just clean this up. And minus k hat is into the page. Oops. So you're doing there. Yeah, minus k hat means into the page. Good, right? So exactly the same strategy for getting the direction as you did in the moving charge direction, right? Now, what if the wire, wires are not always straight. As you can see here, it's a spaghetti of wires in front of me here. So often wires are not straight. Like in this illustration here, you have a crooked wire and you immerse it in a magnetic field region. How will you determine the force that this wire will experience? Yeah, the equation here is showing you an integral of I dl cross B. Well, what this dl essentially means is that if you have a crooked wire, you can always divide this wire into small segments so that each length segment is dl. That's one small length, a segment of length. One small segment of that length can be approximately straight, right? Because if you have a crooked wire and you divide that into small pieces, each small piece approximately looks to be straight, and therefore you can just apply the I dl cross B as we did for the straight wire in the previous examples. Okay, so what this is telling you is that each small segment of wire will experience a force, a magnetic force, which you can calculate, right? I dl cross B, right? So you calculate the small magnetic force experienced by the small segment of length, and then the integral means that you add up all the individual magnetic forces experienced by all the individual segments of the wire. Okay. So that's a strategy to use, but I will teach you a shortcut. Okay, you don't have to cut up the wire into small segments, and you don't have to add up all the forces of those small segments. What you can do is effectively get an effective length over which the current is flowing and use that as the length of the wire that carries the current that experiences the magnetic force. Okay. Right, so by doing so, you don't have to evaluate the integral and you don't have to add up individual forces. All you need to do is find this effective length. Right, what is this effective length? The effective length is similar to the concept of displacement. So you're just looking at 2 points along the wire where you want to find the magnetic force. Say you're looking at these 2 endpoints. The effective length is just the straight line connecting those 2 endpoints, right? So it's exactly the same concept as displacement. You're just considering a starting point and an ending point. Connect those 2 points with a straight line. The length of that straight line will give you the effective length, and use that effective length to calculate the magnetic force in the same way that you calculated the magnetic force of a straight wire. Okay. And if you want proof that this shortcut works, you can work out problem 227-11 in the textbook, and then you will see the proof for what I'm saying, right? If you don't trust me and you want to see the proof, I point you to this problem in the textbook. But let's apply this concept. Okay, how do you apply that L effective, right, in finding the magnetic force? Say you have here a wire. There's 3 amps of current flowing through the wire, but the wire is not straight. It consists of, these segments here. And then the wire is placed in a magnetic field, a uniform magnetic field with a magnitude of 2 Tesla, direction to the right plus I hat, as shown by the arrows here. What's the magnetic force experienced by this wire due to the magnetic field? So 1 square here is 1 meter by 1 meter. So you can use this scale to determine the length of the wire here. Okay, because your wire is not straight, okay, we know that the force is equal to IL cross B, right? Because the wire is not straight all throughout, you cannot apply this equation right away by just adding up all of these segments and taking the total length of the wire. That won't work because this equation only works for a straight wire. Okay, so since your wire is not straight, as I discussed earlier, what you can do is you can divide the wire into segments so that each segment is a straight wire. Calculate the magnetic force for that straight wire segment and do that for each of the segments of the wire. Add up all the forces and you get the net force on the wire. So if you do that, okay, so for this wire segment here, let's call this wire segment 1. Okay, you have the current is 3 amps, so you have 3 amps there, and times the length. Okay, so for the wire segment 1, you're applying ILB, and then the direction plus direction. Right, so the current it carries is 3 amps. That's there, times the length. The length of this wire segment is 1 to 3 meters. That's the 3 meters there, times the magnetic field, which is 2 Tesla as given in the problem. And then for the direction, you do the right-hand rule. Of course, you have I hat, right? Oh, sorry, plus J hat. J hat crossed with I hat, you're crossing in the clockwise direction, so the answer is minus K hat. So this is for the wire segment 1. Okay. For wire segment 2, it's this region here. Notice how it's parallel to the magnetic field. Hence, the force on wire segment 2 is equal to 0. Okay. Wire segment 3 is this segment here. Okay, you again do, so it's not parallel to the magnetic field, so you know there's a force. The current is 3 amps times the length. Length of this wire segment 3 is 2 meters, times the magnetic field, it's 2 Tesla. And then the direction, you have, of course, the current is going downwards, minus J hat crossed with I hat, right? Will give you K hat, but you're crossing in the anti-clockwise direction. So you have a plus K hat for the direction. Okay. Moving on, wire segment 4, that's again 0 because the current is anti-parallel to the magnetic field. And finally, wire segment 5, it's this small segment there. Current 3 amps times the length, 1 meter, times the magnetic field, 2 Tesla. And then the direction will also be minus K hat because your current direction is the same as the first wire segment. So if you add up all of these terms, you'll get 12 newtons in the negative K hat or into the page direction. Okay. So that's the long way of doing it, and you can do that. It's valid, right? The shortcut I taught you is to effectively get the effective length, right? You just want to go from this starting point to that end point. So this blue arrow is the effective length where you want to measure the force. It's as if the current is flowing through this effective length of wire here. Right. Your effective length is diagonal, okay? So there are 2 ways of approaching this. You can either decompose your diagonal vector into the x components and the y components. And you can notice that the x components of the diagonal effective length will have 0 force because, you know, parallel wire and magnetic field has 0 force, but only the perpendicular or y component of the effective length will experience the magnetic force. And hence the force is the current 3 amps times 2 meters. Okay, you might be wondering why the length of the effective length of the wire is 2 meters. It's because it's the length of this y component of the effective length. It's only the y component that will experience a magnetic force because the x component is parallel to the magnetic field. And that's why it's 2 meters. Yeah, that's the trickiest bit there. And then magnetic field, of course, 2 Tesla. And then you do the right-hand rule for the direction. You're doing right-hand rule, J hat crossed with I hat. Or you can also do, you know, if the second alternative solution is to expand out this cross product into the sine theta function, sine theta, in which case you don't have to decompose the effective length into x and y components. You can just straight away substitute values. The current is 3 amps. The effective length is this diagonal one. So it's square root of 2 squared plus 2 squared, right? It's, yeah. And then the magnetic field, 2 Tesla sine 45 degrees. You'll find it will still give you 12 newtons. Good. Right, any question there? Yeah. So the trickiest bit there is if one of the vectors is diagonal, make sure to either use the sine theta definition to get the magnitude, or decompose your diagonal vector into horizontal and vertical components, and only the component that's not parallel to the magnetic field or the current will contribute to the magnetic force, right? All right, so try this exercise, right? It's a problem in the textbook as well. So you have this wire, okay, initially straight, and then it curves with a radius r. And this wire is carrying a current I. It's immersed in a magnetic field region that's pointing into the page, right? Magnetic field is minus K hat. What is the force, magnetic force or net force experienced by this current carrying wire because of the magnetic field where it's located at? You can do it in your head. You can solve this. Yeah, right. This is, yeah, all you have to do is find the effective length. Your current starts here and your current ends there. So your effective length connects the starting point to the ending point of your current carrying wire. Okay, right, and then you apply F is equal to IL effective crossed with the magnetic field. Okay. You can of course expand this IL effective B sine theta for the magnitudes of the magnetic force. Okay. Right. Your effective length, what's your effective length? It's essentially, if that's the radius r, then your effective length is essentially 2r. Right? And hence the magnetic force is the current times the effective length, which is 2r, times the magnetic field magnitude. Okay. And then for the direction, just do right hand rule. I hat current is I hat crossed with the magnetic field in the minus k hat direction gives you a j hat positive. Easy. Yeah. If you want the expanded, yeah, if you look at the textbook has half a page of solutions to this problem. And if you want to look at how they solved it in the textbook using the integral, just look at example 27-3 in the textbook. Good. Right. So what we've learned so far is if you have a wire and that wire has current flowing through it, okay, and you put that current carrying wire in a magnetic field region, yeah, you have here two magnets, North Pole and South Pole. Therefore, there's a magnetic field there, and you put the wire in the magnetic field region. We learned that there's a magnetic force that will be exerted in this current carrying wire, and that magnetic force will essentially tend to rotate this wire so that there is a torque experienced by the wire in this magnetic field region, right? If, yeah, we learn if you have an object and that object starts to rotate, the rotation of that object is because of a torque on that object, and torque comes from the force that tends to pull on that object to rotate it. Okay. The torque that the current carrying wire experiences is given by this equation. Tau, of course, is the torque. It needs a magnetic field because it's only in the presence of a magnetic field where you have a magnetic force, right? And it depends on this mu, which I will discuss later on. But as you can see, it's again a cross product between two vectors, the mu vector and the magnetic field B vector. So the way to work out this equation again is the same way that we've been working out equations with cross products. You can find the magnitude using the expansion of the cross product into the sine theta function. Theta is now the angle between mu and B. So it's always the angle between the two vectors that are being crossed. And then, of course, for the direction, use the right-hand rules as before. Okay, right now, what is this mu? Okay, this mu is a property of a current carrying wire. So if we look at this wire loop, okay, a wire that forms a closed loop, this wire loop that carries a current is called a magnetic dipole, because if you have a current in a wire, this current will generate a magnetic field. And we will talk more about that in our next lecture tomorrow. Okay, that we will talk about a current. If you have a current, this current will generate a magnetic field. So essentially, if you have a closed loop, closed wire loop that's carrying a current, this closed wire loop will generate a magnetic field. We've learned that magnetic fields are generated by magnets. Magnets have a north and south pole, and that's why this current carrying loop is called a magnetic dipole. Okay? Because it sort of acts like a magnet with two poles, north and south pole, which generates a magnetic field around itself. Okay. So this current, if we say magnetic dipole, we're essentially just referring to a current carrying loop or something that generates a magnetic field around itself. Okay. And the magnetic dipole is characterized by what we call the magnetic dipole moment, or just simply magnetic moment, which is the mu that is in the torque equation. Okay. So we can calculate the mu from this definition. It's the number of loops in the wire loop times the current that the wire loop carries times the area of the loop. Okay. Right, the magnetic dipole is, magnetic dipole moment is a vector, right? So that's indicated by these signs. It's a vector, so that means it has a direction. The question is, where do we get the direction of this magnetic dipole moment, or this magnetic moment? So the equation tells us that the direction comes from the area, which is quite weird, right? Because area is just a scalar quantity. But this vector above area is just saying that it's normal. It's a normal vector to the area of the loop. Okay. But if you look at the loop, say this is a loop, it's in this plane, the normal vector can be defined as either going upwards or going downwards, right? Because a normal vector is just anything that's 90 degrees relative to the surface. So you can see that there are two directions for the normal vector. It's either upwards or downwards. So it's ambiguous. To remove the ambiguity, we use the direction of the current to define the direction of this area, or this normal to the area. So by using the current direction and what we call the right-hand rule number 2, where you curl your fingers in the direction of the current and the thumb points in the direction of the magnetic moment, like so. So the magnetic moment is therefore in the upwards direction, and it removes the ambiguity in the normal vectors being pointing upwards or pointing downwards. Right, so we just defined what magnetic moment is, right? So going back to where it all started, if you have a magnetic dipole, essentially a closed wire loop that carries a current I, and you immerse that in the magnetic field region, then your wire loop will rotate in the magnetic field region, and that's essentially how an electric motor works. Because then the torque produced by the magnetic moment and the magnetic field on the current carrying wire loop will cause your wire loop to rotate. And when your wire loop rotates, when you have an electric motor, work is of course being done to rotate the wire loop, and the work done is stored as potential energy. So we can define a potential energy in a wire loop that's rotating in a magnetic field, and we can calculate how much energy is stored using this relationship. Right, the potential energy is a dot product between the magnetic dipole moment and the magnetic field. So that's essentially a negative mu times B times cosine theta. Theta, again, is the angle between mu and B. And as we know, magnetic potential energy is a scalar quantity, and the dot product conveniently gives us a scalar quantity if you apply the dot product into a cosine theta function. So you don't need to determine the direction for the potential energy. Right? Okay, so just putting all concepts together, we've seen that if you have a closed wire loop carrying a current in a magnetic field, that closed wire loop will experience a torque because there is force, magnetic force from the magnetic field. Now the torque of the wire loop or the dipole, magnetic dipole, will only be in equilibrium if it satisfies these two conditions, right? The net force is equal to 0 and the net torque is equal to 0. Right, for a wire loop, closed wire loop, the magnetic force is always equal to 0. Can you see why? If you have a wire loop like this, put it in a magnetic field, okay, the magnetic force will always be 0 because essentially it's a closed loop. It's not straight, so we use our definition of the effective length. Effective length is you connect the starting point to the end point and measure the length of that. But if your loop is closed, there's really no end point and starting point, right? So effective length is essentially equal to 0, and therefore the magnetic force on a closed loop is always equal to 0. So you're now left to determining whether the net torque is equal to 0 to determine whether the wire loop is in equilibrium or not. Okay. And let's look at this example to sort of see, to determine, to see what I mean and sort of bring all the concepts together. So we have this closed wire loop, which is a square with sides 2 meters, 2 meters on each side. It's a square, and it carries a current that's 3 amperes anticlockwise. So the direction is shown here. It's immersed in a magnetic field region of 5 Tesla magnitude, directed to the right as shown in the figure here. Right, essentially we want to determine whether your loop is in equilibrium or will your loop rotate like in the electric motor if you put it in this magnetic field region. Okay. So first we want to find what's the magnetic moment. Okay. Right, magnetic moment is defined as NIA. N is the number of loops. So you only have a single current loop that's square. So N is equal to 1. The current is 3 amperes. The area, it's a square loop. So the area is the side squared, 4 meters squared for the area. So your dipole moment, you know everything, you know N times I times A will be 12 amperes meter squared for the unit. And then for the direction, what's the direction of the dipole moment? It's either up or down, which is the correct. Yeah, you take your fingers, curl it in the direction of the current. You do the curling, you can find that the dipole moment is in the J hat direction. Okay, the direction of the dipole moment is important because you need that to calculate the torque. We want to find the torque. Torque is equal to dipole moment crossed with the magnetic field. Okay, to find the magnitudes, magnitude is of course mu b sine theta. So for the magnitude, you have 12 for the magnitude of the magnetic moment mu times the magnetic field B is equal to 5 Tesla. Right. Sine angle between the current is obviously perpendicular to the magnetic field, right? Because your current is either minus K hat or plus K hat. Yeah, I think in this direction here, you have a current that is in the minus K hat direction. So that will be a sine 90 degrees. Magnitude of torque will be equal to 60 Newton meters. And for the direction, you do right-hand rule. So your current is in the minus K hat direction. Cross that with the magnetic field in the plus I hat direction, right? It's always I cross to B. So you're doing this cross here in the clockwise direction. Hence, the direction will be J hat. Yes, J hat. And you're doing the cross in the clockwise direction. So that's a minus J hat there. Good. So the torque is not zero. Now the potential energy, it's the dot product, magnetic dipole moment dot with the magnetic field. The dot product is, of course, a cosine theta function, cosine theta. Magnetic moment is 12 times the magnetic field is 5, right? Cosine, the angle between the magnetic moment here and the magnetic moment is upwards, the magnetic field is to the right, so that's a cosine 90 degrees. Cosine 90 is, of course, 0, so the whole thing will be equal to 0. Net magnetic force, we said, is always equal to 0 because it's a closed current loop. And because, so type of equilibrium, it's not in equilibrium because force is equal to 0, but torque is not equal to 0. Okay. And I think before we go, I'll just correct something because I saw some mistake here. So the direction for the torque is actually a cross between the, so the direction of the torque here is wrong because the direction of the torque is actually a cross between the magnetic dipole moment and the direction of the magnetic field. It's not the direction of the current. So the direction is magnetic dipole moment is upwards plus J hat for the magnetic dipole moment crossed with I hat for the magnetic field. So that means that the torque will be in the K hat direction, but you're doing the cross in the anti-clockwise direction. That's a minus K hat, right? So sorry about that. Yeah, it's the cross between magnetic dipole moment and not the current. So it's the direction of mu that we need, not the direction of the current. Good. So the magnetic field will tend to rotate the loop in, first into the page, like this in this direction, because the torque is minus K hat into the page. Right. Any questions about this example or the topics we learned today? All right. If there are no questions, then we'll end our lecture. We learned about the force on a current carrying wire and therefore the torque and the magnetic And then we define magnetic dipole and magnetic dipole moments and potential energy. Right, so tomorrow I'll see you in the lecture where we will talk about the sources of magnetic field. So have a good day, everyone, and see you tomorrow.